Okay. Now, whenever we study chemical reaction kinetics, we have seen it earlier that chemical reaction kinetics mainly aims at determination of rate law expression. I'll repeat it. It mainly aims at determination of complete rate law expression. Complete rate law expression means what? Whenever you will be aware about the mathematical expression which relates rate of reaction with concentration, value of rate constant, order of reaction. So whenever this is known, then you say that you know the complete rate expression. Now this rate law expression obtained is used for a design of chemical reactor. Now whenever I am saying design of chemical reactor, it means that what is the volume of the reactor required for obtaining the given conversion or for calculating the time required for a certain conversion if the reaction is carried out in a CSTR, in a PFR, or in a batch reactor, etc. etc. All these calculations can be used or can be done if you know the rate law expression. And that's why it is important. Now, step by step, we'll try to understand exactly what is rate law expression, how it is expressed, and the relevant terminologies associated with the rate law expression. Consider a reaction as shown below. Let the reaction is A moles of A react with B moles of B and C mole of C to give you a product P moles of product P plus say Q moles of Q plus dot 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 like this. Now I have not considered their phases. I am just trying to derive the expression, general form of the rate law expression. Now, the rate law expression corresponding to above general reaction can be written as minus RA. Now minus RA means the rate of disappearance of A. Now generally the reactant which is to be selected should be limiting reactant, which will limit the progress of the reaction, not the reactant in excess. So let A is the limiting reactant, and therefore the rate law expression can be expressed as, say, K C A raised to alpha into CB raised to beta into CC raised to gamma. Now, where minus RA is equal to rate of disappearance E. Generally, for a liquid phase reaction, the rate is expressed as gram moles of the reactant reacted per unit volume per unit time, mole per liter per second. Of course, the unit of time depends upon the nature of the reaction. If the reaction requires many days for the completion, so instead of second, you will be using days. Or if it completes within 1 or 2 hours, you may consider in place of S minute. If it requires many hours, then this may be replaced as in terms of hour, depends. But I have just considered the general case. So rate of disappearance of A. Again, no need to say that A is a limiting reactant. Now K is, so small k is known as rate constant. Now you may ask me, what is the unit of rate constant? Now I will not write here unit of rate constant. Why? The reason being, this rate constant, its unit depends on order of reaction. That means the unit of rate constant for zero order, first order, second order reaction are different. Now, again, I have used one word known as order. You may have a question in your mind, what is order? So that also I am going to explain in a subsequent section. But as I have started with the discussion related to rate law expression, I am just trying to define or state the terms which are written as a part of rate law expression. Now, this alpha, beta, gamma. Now what it is? Alpha, beta, gamma are defined as individual order of reaction with respect to individual order of reaction with respect to A, B, and C. That is with respect to reactant A, B, and C. This power alpha, beta, gamma, which are raised to the concentration terms corresponding to concentration terms are known as individual order of reaction with respect to A, B, and C. Means this alpha is an individual order of reaction with respect to A. Beta is individual order of reaction with respect to B. And gamma gamma is individual of order of reaction with respect to C. But you should remember that in general, whenever we say or we speak that the order of reaction is 2 or 3 or 1, whatever, it is always the overall order of reaction and not the individual order of reaction. Now again, you may have a question in your mind, what is overall order of reaction? So that also we are going to study exactly what is mean by the overall order of reaction. Now in earlier slides, you have seen the general form of the rate expression, the notations, their meanings. There were certain terms which you may have heard for the first time, like individual order of reaction, why it is written, how it is written, etc. etc. And you may be remembering that I told you that whenever we discussed about the order of reaction, then we always talk about the overall order. And therefore, what is overall order? I am not going to discuss any more detail about overall order, but just for the sake of current discussion, I'll be saying something. So overall order is denoted by letter N. Overall order is denoted by letter N. And what is overall order? Overall order N is equal to, with respect to the current discussion, alpha plus beta plus gamma dot dot dot. So if I have to read this equation, I will say that overall order of reaction is equal to sum of individual order. You must be able to recall that alpha is the individual order of the reaction with respect to A. Beta is the individual order of reaction with respect to B, reactant B. Gamma is the individual order of reaction with respect to reactant C. Now, please remember this alpha, beta, gamma, these are the terms which are to be determined experimentally. However, if however if the reaction is elementary, then we can write A is equal to alpha in place of beta, B in place of beta, C in place of gamma, and therefore N will be equal to A plus B plus C. Now, this A, if you remember, was the stoichiometric coefficient of A. B was the stoichiometric coefficient of B. C was the stoichiometric coefficient of reactant C. And therefore, if the reaction is elementary, then for elementary reaction, rate law expression minus RA would have been equal to K CA raised to A, CB raised to B, CC raised to C dot dot dot, where A, B, C are the stoichiometric coefficient of A, B, C in a stoichiometric equations. These are for your understanding. I can rewrite that reaction. A moles of A reacts with B moles of B plus C moles of C dot 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 P moles of P plus Q moles of Q dot 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 dot. So please remember, if it is an elementary reaction, these stoichiometric coefficients are directly raised as the power of concentration terms related to that reactant. So here reactant A, so its power will be A, that is stoichiometric coefficient A. This is B, so its power will be equal to B, that is stoichiometric coefficient. This is C, so power will be equal to C, which is a stoichiometric coefficient. So this A is, in this case, will be the individual order of reaction with respect to reactant A. The small b will be the individual order of reaction with respect to reactant B. The C will be the individual order of reaction with respect to reactant C. And the overall order, as discussed, will be equal to sum of the individual order. Overall order of reaction is equal to sum of individual order. So overall order N will be equal to A plus B plus C. However, for non-elementary reaction, now we can write minus RA is equal to K CA raised to alpha CB raised to beta CC raised to gamma dot dot. What does it mean? It means that for non-elementary reaction, orders are not equal to stoichiometric coefficient. Orders are not equal to stoichiometric coefficient. Alpha is not equal to A, beta is not equal to B, gamma is not equal to C. So in this case, alpha, beta, gamma can be determined from the experimental data. That is, you have to carry out this reaction, take out the sample at various time interval, analyze the concentration of A, B, and C, and used any method of kinetic analysis for determination of the value of K, alpha, beta, and gamma. So at least you must have understood by this time that what is a general rate law expression. So this general rate law expression is equal to the temperature dependent term K and the concentration dependent term and some variables which are known as order are raised to the concentration terms, raised to the concentration term. Now this concentration is the concentration of the reactant, say A, at that time, B, concentration of reactant B at that time, concentration of C at that time. Now at that time means what? The time at which the rate of reaction is measured, right? So we will now try to understand. I told you in the beginning that what is the unit of rate constant, and I told you that unit of rate constant cannot be directly decide because it depends upon order of reaction, right? However, the unit of rate of reaction and concentration are fixed. Say, for example, for a liquid phase reaction, mole per liter per second, and the unit of concentration, any terms A, B, C, it will be mole per liter. Okay, now let us try to understand how to decide the unit of rate constant. Now, we want to determine the unit of rate constant. So, unit of rate constant. Now, I have considered the general reaction, nth order reaction, and therefore I may write further for nth order reaction. Once this formula is known, even by observing the unit of rate constant also, you can decide what is the order of reaction. That we will see once the derivation of unit of rate constant is derived, right? Now, for convenience, for say for reference, the rate expression for nth order reaction shown earlier can be rewritten as minus RA is equal to KCA raised to alpha CB raised to beta CC raised to gamma. But please remember, the unit of rate constant depends upon overall order. So, for the sake of simplification, I can consider another rate expression for nth order reaction. So let the equation is minus RA is equal to KCA raised to N. Now you may say, sir, you have considered 3 reactants and now you are writing just one reactant. Just for the sake of understanding and derivation, I have considered as if there is a single reactant and as if it is an nth order reaction, right? So, so so this is general reaction I have considered as if there is a single reactant and there is nth order reaction. Even though there are other reactants present, but still the unit of rate constant as it is the function of overall order of reaction. So again, even if I have considered if you want, I can write it in that fashion also. Say for example, instead of this, what I could have written, considering the individual order, I could have written it like this: minus RA K CA raised to alpha, CB raised to beta, CC raised to gamma, right? Okay. Now, what I will do is I want to find out the unit of rate constant. So what I will do is I will write it like this. Just try to understand. My in place of minus RA, I can write unit of rate of reaction is equal to unit of rate constant multiplied by unit of concentration of reactant. Now, I may say that concentration of reactant A raised to alpha, unit of concentration of reactant B raised to beta, unit of concentration of reactant raised to gamma. But since there is a common base, that unit of concentration of reactant is common, only power is differing, alpha, beta, gamma. So if we use the concept of the common base and different indices, then we can add them, and that will be equal to alpha plus beta plus gamma. So instead of that, I am writing it as a n. So unit of rate of reaction is equal to unit of rate constant into bracket unit of concentration of reactant raised to n. Concentration of reactant raised to n. And now I am interested in determining the unit of rate constant. Now what to do? There has to be some common variables. Now we have seen earlier that rate of reaction can be expressed as change in number of moles per unit volume per unit time, or it can also be expressed at change in concentration per unit change in time. So I'll just write that formula for your understanding. So general way of writing rate as minus RA is equal to minus dCA by dt. So minus RA is equal to minus dCA by dt. Change in number of moles per unit volume per unit time. So moles upon volume is concentration. So we have considered this as a concentration. Now, as I am writing in place of K as unit of rate constant, because I am interested in knowing unit of rate constant. In place of concentration, I am writing it as unit of concentration of reactant and power order. So in place of unit of rate of reaction, I can write unit of concentration divided by unit of time. See, this DCA means what? Concentration. So say for example, 10 kg minus 5 kg. How many kg? 5 kg. Like this, change in concentration. So final concentration minus initial concentration. But again, the value will be in a concentration units only. So in place of unit of rate of reaction, what we will write it? Unit of concentration divided by dt, change in number, the time interval. So unit of concentration divided by unit of time. So unit of concentration divided by unit of time is equal to unit of rate constant multiplied by unit of concentration of reactant raised to n. Continuing our earlier discussion, so in place of rate of reaction, what I can write is minus dCA, that is, now we will not consider sign. So unit of concentration minus dCA divided by dt, so unit of time. is equal to unit of concentration divided by time, unit of time. So now unit of rate is equal to unit of rate constant is equal to unit of concentration, unit of concentration raised to n. You may write it completely also, unit of concentration raised to n. Now you can see unit of concentration and unit of concentration raised to n. And so we will shift all the similar variables to one side and the unit of rate constant to another side. So I can write it like this: unit of rate constant is equal to unit of concentration divided by unit of concentration shifted from this side raised to n multiplied by 1 upon unit of time. And you are aware that power base is same, powers are different. Here the power is 1, so this I can write it as unit of concentration raised to, now here power is 1, here power is n, so a raised to x upon a raised to y, so a raised to x minus y, so unit of concentration raised to 1 divided by unit of concentration raised to n, so unit of concentration raised to 1 minus n, and this unit of time I can take it in a numerator, so unit of time raised to minus 1, and what it is unit of rate constant. So in this way, we have derived an expression for unit of rate constant for nth order reaction. For nth order reaction. So above equation, above equation, above equation is useful for calculating unit of rate constant for nth order reaction. Above equation is useful for calculating the unit of rate constant for nth order reaction. We'll see some examples how this general equation for determination of the unit of rate constant for nth order reaction is useful. Now, just for the sake of understanding, consider the first order reaction. Consider first order reaction. So, n is equal to 1. Now, we have just derived the expression that unit of rate constant is equal to unit of concentration raised to 1 minus n into unit of time raised to minus 1. Now, if for it is a first order reaction, n is equal to 1, so n is equal to 1, so 1 minus 1 will be 0. Anything raised to 0 is always 1, and therefore for n is equal to 1, the unit of rate constant will be equal to unit of time inverse, that is time inverse. Now suppose if you read any problem statement, and if unit mentioned are second inverse, minute inverse, hour inverse, you can see this inverse, second inverse, minute inverse, hour inverse, or time inverse, it means n is equal to 1, that is order of reaction is equal to 1. Now suppose if n is equal to 0, if n is equal to 0, then if you substitute n is equal to 0, then unit of rate constant will be equal to unit of concentration. Now 1 minus 0, so concentration raised to 1, and unit of time raised to minus 1. So you concentration per unit time, see this minus 1, you can take it in the denominator. So unit of concentration divided by unit of time, unit of concentration divided by unit of time. So this is nothing but the rate of reaction, and therefore from this I can say that for n is equal to 0, unit of rate constant is equal to unit of rate of reaction. That means unit of K is equal to mole per liter per second, or mole per liter per minute, etc., etc. So if you find the unit of K as mole per liter per second, you can assume that it is the zero order reaction. It is the zero order reaction. If the unit of rate constant is equal to time inverse, you can assume that it is the first order reaction. Now again, consider n is equal to 2. So unit of rate constant as per the general formula for unit of nth order reaction. The general formula for unit of nth order reaction is unit of rate constant is equal to unit of concentration raised to 1 minus n into unit of time raised to minus 1. Therefore, unit of rate constant is equal to unit of concentration is generally mole per liter, n is 2, so 1 minus 2, and unit of time say second, so minus 1, and therefore it will be mole per liter raised to minus 1 second inverse, and therefore if you write it properly, then it will be liter per mole per second. So if unit of rate constant, if unit of rate constant is equal to liter per mole per second, then you can directly say that the reaction is second order. If the unit of rate constant is time inverse, you can directly say that it is a first order reaction. If unit of rate constant is uh, similar to the rate of reaction, that is mole per liter per second, then you can say that it is the zero order reaction. So in today's session, we have tried to understand the general form of the rate expression, what is mean by overall order of reaction, what is mean by individual order of reaction, how the rate law expression is written for elementary and non-elementary reactions, and how the unit of rate constant is dependent on unit of concentration, uh, unit of time, and order of reaction. And we have also tried to, I have also tried to demonstrate how the unit of rate constant differs with respect to order of reaction. If you just have a look at what has been taught so far, then probably you will be able to understand it very, very easily. Now, even though this last part, that is unit of rate constant, seems very easy topic, but if you are solving some problems related to determination of order of reaction, then if the value of unit of rate constant is given, then from that value itself you can guess where what might be the order of reaction. And if you get the same answer, then you can say that your calculations are correct. If you don't get the same answer as indicated by the unit of rate constant, then you have to recheck your solutions. So with this, we'll end this session. I hope whatever I have tried to teach you, you must have understood. Thank you very much.